Hello, I'm Dr. Greg Strimmel, Assistant Professor at Purdue University and the Director of Transformative Research for the AE Research Collaborative. And today I'm here with our friend, our colleague, Dr. Michael Grubbs, Coordinator of Career and Technical Education for Baltimore County Public Schools. Mike, would you tell us a little bit about your schools and maybe the state of engineering learning within those schools today?
Sure. Thank you, Dr. Schimmel. I currently am the coordinator of career and technical education for Baltimore County Public Schools. We have roughly 24 high schools in Baltimore County. Our school system borders the Pennsylvania line and goes all the way down into Baltimore City. Out of those 24 high schools, we have a variety of technology and engineering education experiences. We have programs that are at comprehensive high schools. We have programs that are at regional magnet programs, and we have programs that are in our shared time center. In these experiences, we're really meeting students with a variety of background, and we're trying to address multiple needs. We're trying to provide engineering for all students. Every single one of our students in our high school programs. We're also trying to meet students who are entering two-year programs after high school, such as the community college. And we're also trying to prepare students who want to go on to that professional engineering pathway after high school, the University of Maryland, the Purdue's, the Virginia Techs. And so when we think about curriculum for Baltimore County Public Schools, we're really trying to meet multiple stakeholders. And so currently, or really up until the past 2 years, we offered engineering curriculum that was aligned to vendors and what was available, such as Project Lead the Way, curriculum such as the International Technology and Engineering Educators Association, Engineering by Design. And as great and useful as those programs are, we didn't have opportunities until a few years ago to write our own curriculum for one of our magnet programs, Eastern Technical High School, on the eastern side of Baltimore County Public Schools. And so what that gave us was an opportunity to consider what was out there for K through 12 engineering, where we wanted to begin, and consider some next steps for addressing a need to rewrite engineering curriculum at the high school level.
So let me ask you a follow-up, Mike, about you mentioned your own programs and having that opportunity to essentially write what it is that you need. So what is the value and the benefit and the need for doing your own programs?
Yeah, great question, Dr. Shermill. So right now we're looking at a program at Eastern Technical High School, and we're trying to meet the needs of those students. And when we look at national curricula, that national curricula is written to meet needs of industry and prepare students from all over the country. And when that happens, it's not necessarily designed for students in a specific region or a specific high school, as I mentioned, a magnet school versus a comprehensive high school. And so when I went about looking at Eastern Technical High School and starting from scratch, we really need an opportunity to look at those students, look at how we're serving them, and considering where those students are going after high school. And we needed resources, and we needed ideas and examples where we could modify those to meet the needs of our students, and more specifically, our teachers who wrote the curriculum and write the curriculum and had a good understanding of where those middle school students were coming into the program so that they could tweak their units and their curricula and their lessons, not just take something that was written at the national level that was canned or cookie cutter and just directly implement it at the K through 12 level. So we really had a need for something that from starting from scratch, but we needed to also build upon, not just take something and just do it verbatim. So we're really looking for something that was a flexible approach.
So as you know, and as you've been involved with the AEEE Research Collaborative over the last few years, we've been developing a framework for P12 engineering learning. And as part of that, you know, I wanted to see your perspective on why such a framework may be needed to do that type of work in the schools. Any thoughts on that?
Yeah, great question. So spend about a year, maybe a year and a half looking at the existing curriculum at this specific school. And one thing I want to note is, although this was a magnet program, the idea is down the road we would expand beyond our magnet programs to our comprehensive high schools, to our individual courses. So the focus on the magnet program is just the beginning. It was a quick win. It was a timely situation. And as we looked at what would we write, where would we begin, I quickly realized, and by engaging with the group at AE3, is that there was nothing out there. There was nothing out there for K through 12 educators to write curriculum. Sure, there were standards documents such as the Standards for Technological Literacy. There were documents that talk about habits of mind and the next generation science standards. And all those documents were influential in the backwards design and mapping the curriculum, but nothing truly addressed what engineering content was at the K through 12 level, specifically the high school level. And so what I really needed was, as I worked with our curriculum designers and our teachers and our writers, was to understand what's the content that a high school student may or is expected to understand as a result of coming through this program. It's kind of a menu, not these are the things they must do. This is the design process. This is the engineering content, but more of these are expectations of a high school student, whether they're just trying to get some problem solving skills to be better democratic citizens, whether they're going into the workforce or a 2-year community college degree that's articulated with our program, or they want to go on and be a professional engineer and go to a 4-year institution such as a Virginia Tech or a Purdue, for example. And so what I searched for and we're beginning to find was a seminal document that outlined what engineering content knowledge was. What are those core and sub concepts that teachers can use and can think about to write their curriculum? And up to this point, there has not been a document that covers that.
So then maybe just a little bit of a follow-up. How do you think that that document could actually influence the work or is influencing the work that's currently being done?
Yeah, great question. So where we've sat over the last few years is we've used some of that preliminary document. We've examined some of the proposed concepts, and instructors have considered where middle school students are coming in to write the program. What concepts are missing? So it's been a form of gap analysis, a diagnostic assessment to understand where students are coming in, both collectively and individually. How do we work on pre-assessments and formative assessments to raise that bar and serve them better? Because at the middle school level, those engineering experiences are spotty at best. Some students have a strong program, some don't have any program. And then it's also helped the instructor understand, how do I continuously raise the bar for the students? How do I assess where all students are and move them along a trajectory or a progression of learning to immerse them in situations that are rigorous and increasingly challenging for them, so that I'm not just providing them floor level concepts. I'm raising the ceiling, I'm teaching to the ceiling. And so these concepts and this framework have and will continue to be very influential in our work to write curriculum and be responsive to students' needs. And not only students' needs, but also true alignment to post-secondary experiences, community colleges, 4-year institutions, the industry, which is really, really important that we're providing concepts that are not contrived or limited to just our technology and engineering education stakeholder group, but also the larger professional community. So the terminology that they're learning in their classrooms does carry over into the institutions that or experiences that they then go into.
Yeah, thank you. We all seen some of the activities, the same activities done over and over again in classrooms. Build a tower. You see it at elementary school out of kind of unrealistic materials. You see it in middle school, the same thing, and then you see it in high school, the same little tower. Build the tower the tallest and put the most weight on it, and being those titled as engineering activities without that scaffolding to go a little bit deeper. I think that's what you were hitting on, and also with the authenticity to engineering, um, to really to address what that is to get to that level. Do you have any thoughts further on that influence as far as being able to do some type of progression and scaffolding beyond just the traditional activities every
Yeah,
year?
yeah, great follow up. Really, at the core of this work was what you brought up. When we looked at the curriculum and we saw juniors and seniors were doing popsicle stick towers, and there was nothing wrong with that, right? That still stayed in our curriculum. The concepts and the framework has helped us have honest conversations around truly where those experiences fit in and why we put them in there. So, a junior and a senior who is for the first time doing a popsicle stick tower has now been moved to an introductory concept in the freshman year, and the intent isn't just to learn about live loads or dead loads, but it's also to learn about collaboration and teamwork and material choice. And then that's allowed the conversation to then look back to the learning progressions and look at things like material and processing and quantitative analysis. And so the junior and senior year is much more rigorous, and they're using more authentic materials. And so I think it allows us to have the best of both worlds. Those low tech problem solving experiences around the habits of mind, and then also a deeper rigor, more rigorous experience as they matriculate through their sophomore, junior, senior year. And so when we look at materials and resources in the curriculum, we've been we've been more deliberate in the materials we're purchasing for the program and the experiences that the students are doing. And the framework is really helping to ensure and distinguish from other programs the depth of the experiences that they're going through.
Great. So I'm just going to end with this last question there. So you've been working with your schools and some teachers there to leverage some of the early versions of the framework that we're discussing. So can you give any just quick examples of what are they doing now that that is different than before because of how the work's been informed, and how does it look like a different engineering learning experiences than what has been titled that in the past?
Yeah, great question. I have a few examples. One that really comes to mind is around quantitative analysis. And the teachers at our program have really reflected on the mathematical and predictive analysis and modeling and computational thinking and reasoning that was happening in the program. I'll say pre-framework or pre-framework conversations. And so we saw examples in the previous curriculum that was Excel based or basic level math. And what we're seeing now is that the teachers are trying to incorporate more of examples such as MATLAB or higher level rigor in terms of mathematical analysis, and looking at the concepts that are maybe middle school level and amping them up so that they're more aligned horizontally and vertically to our math department. And the quantitative analysis components and the rigor behind the engineering framework uh, has really helped our teachers reflect on what they're putting into the curriculum. Some other examples are around just brainstorming in the design process. I think the design process up to this point has been taught very cyclical, and it's been taught very surface level. The learning progressions have allowed the teachers or encouraged them to look at a greater depth, look at ideation on a deeper level. Um, Thinking about, well, I'm not going to just give students come up with two or three different ideas. The learning progressions have forced them to really think about what is ideation and how do I purposefully or deliberately teach it. And so they're looking at things like design heuristics. How do I truly teach brainstorming and ideation? And the learning progressions have sparked that conversation. They haven't provided every single answer and they weren't designed to do that, but they have been very helpful in taking all the core and sub concepts and having our teachers be more deliberate in taking students through the various levels to get to a point where there is engineering literacy and they feel confident in speaking to the engineering habits of mind and content base. So those are just a few examples of things that we're incorporating and expanding upon in the curriculum that I don't think would have happened if we didn't have a framework for them to really start digesting and thinking about the depth of the lessons and instructional resources that they are putting into their curriculum.
Well, thank you, Dr. Grubbs. I appreciate your time today and some of the examples you provided. Hopefully that could be helpful to the audience and to see some ways to re-envision some engineering learning happening in the schools. So thank you for your time. I will remind everyone that you can go to p12engineering.org and access some of the materials and get some preliminary work and the framework materials there too. So thank you, and we'll see you later, Mike.
Bye. Thanks, Greg.